Okay, I think it's gonna record. All right, let's get going. This is what we did last time, and this is the exercise that you did. So we introduced numerical methods for solving ordinary differential equations. We're gonna have them in the form dy dx is f of xy. X is a variable, and we are looking for a function of y as a function of x. Okay? And we typically have initial boundary problem. That means that we have one of the values at the specific x, we have a given y, and that's our starting point. Given that starting point, all of the other y values we will find by first we will design ourselves a little grid of x values, okay? However many you like. We typically do them at a spacing, at an equal spacing h. Okay? And then for every y, starting from this starting one that we call x1, y1, starting from that point, we basically say, okay, according to the simplest of them all, the methods, we say, like, take the previous value, take this slope estimate, because this is dy dx evaluated at xi, yi, according to this. Take this slope and take it for distance h, and this is your new predicted value. And then with that value, you keep going, so you can actually create a very simple loop that will do that, and most of you have hopefully completed that last time. And when we actually look at the various solutions for different h, as my h is getting smaller, I'm going to get closer and closer to the analytical. In this case, we had an analytical solution, so we could actually check how well we're doing. In most of the cases of interest, you will not have that analytical solution. You will check your method in a number of cases where you actually know. This is what you know from your ODEs class. So basically, you will check how well you're doing in the problem that you know the solution for, and then after that, you trust the method to work well. Now, this is Euler's method. It's the simplest method. It's not the most accurate one. There are more accurate ones, and it's really about how do I estimate that slope and how well I'm doing in estimating that slope. Really, practically, if you remember the way I got the Euler's formula, it's really taking first two parts of my Taylor series. Okay? So if I say here, this is basically y at xi plus 1, right? Which is y at xi plus h is equal to y at xi plus dy dx at xi y1, right? Times h. So this is actually the first two terms in Taylor's series with everything else chopped off. You can actually get more and more accurate the more terms you get. Okay? And you can actually really tweak this slope using Taylor's series formula. We're not going to go into details of that, but basically a lot of the methods afterwards are done that way. One simple modification is so-called Hoyne's method. Basically say, okay, I'm going to take this first slope, f of xi, y of I. Then I'm going to take the slope at a point where my Euler's method would predict that this is my next point. I will, instead of taking that point, I'm going to take a slope at that point, and then average these two slopes and get a little better estimate of my slope. So essentially, my method will go as I so-called get a predictor. This is essentially my Euler's solution. I will then evaluate slope at that solution, and I will average my first slope and the second slope, and this is now the slope that I'm going to ultimately take times h. Okay, that's one way. And then trust me, there is 50 other ways to actually do that. Ultimately, they're all actually called so-called. So Hoyne's method will actually improve a little on Euler's for the same h. It's going to behave better or be closer to the true solution. And we're going to do an exercise to prove that. But there is so-called one of the best methods. There's a whole class of methods called Runge Kutta. they all look like this. So they're going to estimate this slope or increment function is basically weighted sum. Your weights A1, A2, and so on are given. So those are the numbers you have. And you find K1, K2, Kn as follows. Your first one, K1, is the first slope. That is always the slope from Euler's, really. K2 is basically Euler's at a slightly different point. Okay? And you do need K1 to actually find this K2. And these numbers P1, Q11 are given. So that's something that you have. And then you keep going. You can actually keep going like that. And one of the most famous ones is so-called Runge Kutta, which basically takes K1 first slope as Euler's. Then I go 1/2 h, and I estimate slope there. I estimate the sort of a solution assuming this slope K1. Okay? And that, I find the slope there, so that's my next slope. Every time you evaluate f at a point, you're finding slope because dy dx is f. Okay? Then you also do the same by taking slope K2, and you evaluate the slope at that point. And finally, you go all the way by h, and you take slope K3, and that's your final. So then I have 4 slopes. Okay? Again, all of the coefficients are given. I know what h is, and once I have K1, I can find what K2 is. Once I have K2, I can find what K3 is. Once I find K3, I know K4. And I will take this weighted sum. So sum of these coefficients is always 1. So you say 1/6 of K1 plus 2/6 of K2 plus 2/6 of K3 plus 1/6 of K4. Proof that this works is in kind of a Taylor's analysis. That's beyond what we can do in this class. But basically you analyze Taylor's expansion and you find that this is actually almost 4th order accurate. That means that in Taylor's formula, first 4 terms disappear, and the whatever's remainder is O of h to the 4th. So as h goes smaller, that really drops down really fast. It goes to the 4th of that. And we will actually today do an example where you actually, if on that very first problem that we had, this was like Euler for h is 0.5. If you do Runge Kutta 4th order, okay, for the same 0.5, you're right on the money. Okay, so it's really an accurate method. Now, before we get to try them out, what are you expected to know? Essentially, the moment, so here's going to be the exercise we're going to work on today. Essentially, for ordinary differential equations, you need to know that the way we are getting them is by estimating these slopes. Okay? And every sort of a better method is just a better estimate of that slope that I'm taking at a point to take me to the next point. Okay? And there is basically numerical background to how these slopes are chosen. It's not that you pull them out of thin air. Okay? Now, if I give you a formula like this, I expect you to know how to program it. It's really a formula. So in that sense, I expect at this point that you have a level of expertise in programming, that I give you a formula even if you don't know what it is. Okay? You can just like, here's the formula, compute. You can do that. Because at this point, you can take whatever you had for Euler formula and then modify it slightly, or not so slightly, but you can essentially just amend your for loop and step in and get it improved. So it's somewhat detached from understanding what are you programming. It's actually a skill in the program. Okay, here's the formula. How do I implement it? So there are 2 levels in this class. I do expect you to understand a little bit about the methods themselves and how we got there. But there's also just the practical part of implementing methods on the computer, using the tools such as for loops and while loops and so forth that we use. So this is going to be an exercise. I just want to comment on one more thing, is that we could be also solving systems of ODEs, and whatever we talked about solving one ordinary differential equations, it actually applies to a system. So if I had a system of two, not just one, I have dy dx, I might have another function, z, okay? And both of them depend on x, okay? Because they somehow interact, but they also depend on each other, okay? This, you can actually assume a situation where you have lions and gazelles, predator and prey. So of course, how many predators you're gonna have depends on how much food they have. How much gazelles you're gonna have depends on how many lions you have. There's a death rate for both. There's just a death rate by nature, but there's also death rate by lion for gazelles, okay? So it depends on how many lions need their food. And for lions, well, they just died. Maybe we can involve humans. They kill off some lions. So you could have a very complicated systems, but even if you just had two things that are interacting, they're not depending just on their own population, they're also depending on outside influences and interacting. So you could actually have a rate of change in either population that depends on that population only and some other. So they're coupled. It's called coupled equations. So how do I solve coupled equations? First, I have to model them in some way. In this case, we actually have that the rate of change, growth or decay, there's a birth rate of lions times number of lions. Okay, so this gives me how many more lions I'll get per year. Times number of gazelles, well, because they depend on gazelles for food. Whoa, hi, excuse me. I'm just gonna kill this. Okay, close tabs. Oh, go away. Okay, sorry about that. My phone calls come to my computer. Especially when my phone is not with me, so I'm not answering the phone. So, all right, so basically we have, so there's death rate and birth rate, but I also depend on how much food I have, okay? And for number of gazelles, I have the birth rate, but my death is very much related to lions, okay? So basically they interact together, so I need at each point, I need both number of lions and number of gazelles to find my number of lions, and the same for gazelles. So these are so-called coupled equations. Now how do I discretize them? Actually, so this is formally saying that my dy dx is some function of x, y, and z, and my dz dx, okay, is some function of also x, y, and z, a different function. So the way I would discretize this, at every step, I'm going to solve for 2. Okay? If I had Euler's method, I'm going to say my yi plus 1, okay, is yi plus this first function at my previous step, xi, yi, zi, that I have from previous step, or my initial condition, times my spacing h. And zi plus 1 is zi plus f2 of x, I, yi, zi. So again, this function f2 at using my previous values times h. If I had 3 or 4 or 7 equations that are coupled like this, doesn't really matter, procedure is the same. So, of course, Euler's method is the simplest method. I could use Euler's method, I could do any other method. It's just going to be a much more writing, so if I actually had my Runge Kutta, okay, then I would have to do Runge Kutta for both, and I had 4 equations for y and 4 equations for z at the same time. Okay? Again, a little more writing, but any method that you have for single equation, you can use for system of equations. All right. So basically, you have a lot of practical problems. You could have more than 2 ODEs. You could have any number of ODEs. And Euler's method would be the simplest, but you can do any higher order method. Okay. Now, one thing, again, as I pointed out in this class, there's the programming part of this class and the logic structure of how do I use the computer to help me unsolve the problems. Because for the most part, we want to use computer for those problems that I don't want to do by hand. Okay. And we learned MATLAB, okay, but any programming language will do. So if down the line in your career you need to use a different programming language, that doesn't matter. Like it could be Fortran, it could be C, it could be C++, all of them will have for loops, while loops. They'll just be written slightly differently. And they will have different ways to, we talked about arrays. All of these programming languages will have some ways to store arrays, so, or other data structures. So you just, basically you're primed now for learning any other language that you will probably need down in your career, because your careers will be 30 to 40 years long. Okay? So MATLAB will probably not be in 30 years from now. We'll teach you something different. Okay? I didn't learn MATLAB, well, it just started a long time ago. Okay? So it's things generationally change. Now, numerical methods in themselves, you've seen so far that none of them always works perfect. So there's a little bit of art there of finding the method that works well for the problem that you have. So for that, you kind of need to estimate the accuracy. You need to have some problem that's going to be your test problem. And then after that, you kind of trust the method and you figure out. Now, you'll always have some error. But given that we're in engineering, and especially in petroleum engineering, you will find yourself often that if you're in the same order of magnitude, you're good sometimes, okay? So you don't have to be super, super exact. You can still solve the problems and move on. So with that comment, sort of like on the general scope, I will go back to our problem today. So our exercise will be to solve the same problem we were working on last time. So this was the problem. Where was it now? This was the problem. So start, please, from the code that you already have. Okay? And I want you to modify that code to actually solve it both with Hoyne's method. And this funny pronunciation I have is because this is a German, both Euler and Hoyne are German names. So this is the Hoyne's method, and this is the Runge-Kutta method. So I want you to program these two methods. So maybe you want a separate routine for Hoyne and separate routine for solving Runge-Kutta. Call it however you want. And I want you to execute those two. And I want to compare Hoyne with 0.1 for h is 0.1 with Euler for h is 0.1. Okay? And I want you to compare, and basically Hoyne is actually right on top of the analytical solution, as you can see. And same will happen for Runge-Kutta fourth order for h is 0.5. It will be much, much better than Runge. Okay, so I want you to make that comparison.
Do we make new functions?
Yes. So you start with whatever you had for Euler and you modify it to work with these two. And I'll walk around and the U is available as well. Yes.
H, comma, Y, I. What is that referring to?
H, comma, Y, I. Oh, it's K1 times H. It's not comma. You compute K1.
The one to the left.
Here. So this is evaluated at this point and this point. So f is a function of two variables. This is your first variable. So you move halfway to your xi, I plus 1. Halfway there is this point. And at that point, and you take this slope at that point. Okay? So evaluate slope at this point that is sort of halfway. Okay. So that's your slope number 2. So graphically, if you want to, so this was your slope K1, Benjamin. This was your slope K1, okay? So you took that slope only sort of halfway, 1/2 h. And this is your prediction for y at that point. So you evaluate f of this x point and this y point, which is the slope at that point. So that's your second slope. Okay. and then you find the third slope and fourth slope, and your ultimate slope is sort of a weighted average of these fourth slopes. And again, these coefficients are, you can, if you throw them into Taylor's expansion, they're gonna kill all of the first four terms, and you're gonna have a very accurate method. Whatever is left is O of H4. Everything in before that zeroes out, and that's what makes it accurate. Okay. And if you ever need to practice implementing more methods, there's a slide that gives you all kinds of more methods. Hint, hint.
What hint? I missed the hint.
You missed the hint. If you ever need more practice with more types of methods, there's a whole slide with different Runge Kutta methods.
Oh,
I can kind of bet you that one of those will show up on final. Kind of.
yeah.
So, kind of.
Let me take a note.
Yeah, write it down, please, so you don't forget. All right, this is the exercise for now.
So on their final, when is their final?
The final is Tuesday after that other weekend. So it's, well,
Is Monday a final or is it another class? Is Monday a final or is it?
there will be a short review, so there will be a short slot and then we'll do one exam. It's not going to be much easier. I'll post something.
Is it gonna be cumulative or just the?
Well, so you can see, so we did all these with the big curve fitting. There will be certainly a full problem on curve fitting and a full problem on one of these larger problems, right? I don't think I'll have more than 6 problems. So normally we had 5. So it's not gonna be a full 3-hour final. I'm gonna aim for shorter. I don't think it's human, right?
So
Well, yeah,
Monday?
maybe grad.
No, it's on Tuesday.
Actually, grad is Tuesday. 3 hours. Actually. So there will probably be 6 problems. So there will be some selection of the previous material. And we'll have, and I think I'll introduce very shortly integration. So there will be probably a very simple problem on integration, one on curve fitting, one on these. And then something to do with systems of linear equations. No. And since we didn't do iterative methods of midterms, so there will be one problem with iterative methods. And then the other 2 problems will be some review from this one in some form. So I can't review everything. Yes.
Do you know where? Where?
I have that somewhere. No, I can find it though. What is our unique number?
19045.
Thank you. December 13. WRW 102. Where's that? Woolrich Labs.
WRW.
I still don't know where that is. Okay, 24th. Oh, that old building. Okay.
102.
Yeah. I've never had a class in the exam in that building. All right. So WRW 102.
I have 2 finals in the same year.
Yay for you. Xn is your endpoint. So yes, that's up until you go. So that decides how to discretize the problem where your x's are, right?
And are we using the same function loss exercise?
Hmm?
Using the same function.
Yes. So same example. Because I want you to compare how accurate those methods are. That's kind of the whole point. So when you will be solving down the line a problem, you probably want to play with a number of methods to see how well they're doing.
The same thing as the exercise demonstration. This one uses maps for. Yeah, we do use the if you have a big file,
Yeah. Oh, I thought
exact same function.
in the graph you mentioned today?
Yes, I'd like it to. Okay. That's the whole point. It's just one more clock.
Yeah.
And by now you're experts in plotting, aren't you?
Of course. That's the one where oh, okay. Not that one.
It's really much at
Okay, so
Yes.
Oh wait, how much scatter? We're not finding the Euler.
We started writing another. No. You can have a say or something. Anybody else has problems with
Wait, I haven't defined it. Can you give us variables at first? Maybe, yeah. Hey, watch your language.
Oh, here. Yeah, in this class.
Is that most of it? Is that a lot of it?
So do I need to move this function outside?
Nice. Yes, it's very obedient. Essay.
That's weird. That's weird. I mean, it's a different, but yeah, you could say that and do that. My other ones were way. There's no why. Well, because we have y vector of 0, with exception when we have y1. So like you start by 1, you have I2, now you start
Well, you can. I just like, all I did was just basically I did I just changed the apples.
Maybe that's you just is that same
In this case,
but there is love.
Was he the best one on the soccer team?
so at this point, I'm gonna leave the class. So this is my
Sean's win. That means you suck, you got these. I would think upper body strength.
I need to
I want you to hear that. I want you to get up to the full workout. Yeah, dude. There's no way you
yeah. One thing. Is that your Wayne graph or your just when one we're doing what is oh, I didn't oh, you should but for what for this, which is why you would have 81 Sean told me yesterday that he had really Hey Sean, I said you're going to what is that? 1.75? I wore this month for his birthday. Hey Sean, Please fill out the survey. And when you return the survey here to Sir Lance, you will sign the sheet. And you can leave these sheets at the front, and I will enter a quiz grade based on this. Okay? I have to leave the class while you're filling out the survey. Yeah. Right. You can just bring me the.
Professor?
Yes.
So they fill out their names
Yes.
after they're done?
When they're done.